these transformations preserve the order, I'll say, in time. Okay, so what this means is if I've got 2 points and they're related by some geodesic, really, then if that geodesic is time-like, then what I do is I take this Lorentz group element and I apply it to that. And if you're in the kernel of this map psi, then that geodesic is still time-like. So that's nice, physically. It's got a lot going on. Okay, and S, so you know what O13 is, you know what SO13 is, you know what O up 13 is, the orthochronous Lorentz group. And then SO up 13 is just the intersection of these two things. So SO13 intersected with the orthochronous Lorentz group 3, like this. Okay. I think I'm going to go 5 minutes and more, and then I'll stop. No, I think does it tell you on the tape? I think I've got 5 minutes left.
Yeah, you got 11.
Okay. I think this is quite good stuff. Okay, so this is going to be, when I read this the first time, I was excited. I really started to understand this deep area of physics that I didn't get. So I hope it does the same for you. Let's look then at the orbits of SO13. Did I tell you what this is called? No, I didn't. This is restricted Lorentz group. I forget this. Yeah, restricted Lorentz group or proper Lorentz group. It has 2 names.
But so the arrow tells us that it's in the kernel, and therefore the determinant is 1.
The arrow actually tells me it's in the kernel of psi. So before I was looking at the kernel of the determinant map. Now I'm looking at the kernel of this different map, which just looks at the upper left-hand entry of the matrix and looks at the sign.
Right.
So the sign's either positive or negative.
Right.
And what this says is these are really all the matrices. This is a technical way of saying these are all the matrices. O up 13.
Right.
Are all the matrices with a positive entry up here.
Okay.
That's it.
Okay.
Okay. Why didn't I just say that? Okay. So, yeah, the orbits. So, let's just go ahead and look at the orbits. They're really, I'm just going to say this in words because I don't want to belabor these points. There are 2 natural actions. One of them is called, there's the identity action of these groups on R4. Just apply the group. They're already matrices. Just multiply them by the vector and you get a new vector. So that's an action already. Okay. But then there are other ways you can take, this is a group, you can, there are other actions you can define. Okay, and that's the subject of representation theory. And that's really important because you want to look at all these actions. Sometimes there are these symmetries encoded in your physics, and this is how you find them through representation theory. Okay, so but we'll look at just the orbits, and I'll make this. But we're going to look at orbits of SO3 acting on not R4, but R4 star. Dual space. Okay, and really this has the effect physics-wise, it has the effect of, we're going to apply this to the momentum space. Not the coordinate space, but the momentum space. And mathematically, this is called a contragradient representation. And we can talk about all these things if we have time before the end of the semester. Okay. It turns out that the orbits of the restricted Lorentz group are equal to just the orbits of the orthogonal Lorentz group, and so this is a big deal, and then parameterized by something I'm going to call, by this number m. Guess what? It's the mass physically. Okay. Here are my orbits. There's one that's given by this. And now instead of, these are going to be the names for my vectors. I'm going to call them p. This is p squared equals m squared not greater than 0. Okay. Second, I'm going to write these down and then talk about the geometry that's related to this. P squared equals minus m squared. No, that's later. Okay, this is positive m squared again, and then p naught less than 0. You've got y, this is a capital Y, so m is going to be all the points p with p squared equals minus m squared. Okay. And then you've got another orbit right here, which is the identity. Okay, that's that. Okay, here mass is allowed to be 0, 0 to infinity. Mass is allowed to be 0 here. Mass is not allowed to be 0 here. And here there's none of this. Okay. What is the p? The reason that we did all that mess with the indices last time is partly so that we could talk about this thing. So p squared, this is, p such that. P, remember, p are going to be the vectors in R4 star. Instead of calling it, it's the same, think of it as R4, regular open Minkowski space. So when I look at p squared, that's going to be really p mu. All right, so don't forget that that's p 0 minus p. I'm going to write it like this, p dot p. All right. By the way, p0 is the